Okay, so this is FRQ Set 2, and in this session, we are only going to go through the first four problems. The next two, numbers 5 and 6, will be assigned on a different day, okay? All right, so this says a graphing calculator is required for some of the problems or parts of the problem, so go ahead and make sure you read through and see which ones need a calculator. All right, this one, I believe you need a calculator. So it says, let f and g be the functions given by f of x is 1/4 plus sine of pi x, and g of x equals 4 to negative x. Let R be the shaded region in the first quadrant enclosed by the y-axis in the graph of f and g. So here's R, right? And let S be the shaded region in the first quadrant enclosed by the graph of f and g. So this is S. So there are two different functions. Number one, find the area of S, and number two, find the area of, number one, find the area of R. Number two, find the area of S. Number three, find the volume of the solid generated when S is revolved around the horizontal line y equals -1. So first thing you want to do is find out where they cross, where they intersect, because there's two intersection points. Here's intersection A, point A, and here's intersection point B, right? So using your calculator, you got to graph these two and find the intersection. So I'm going to jump over to my graphing calculator. All right, so make sure it's on Cartesian or a normal graph. So 1/4 plus sine of pi x, right? And the second function is 4 to the negative x, okay? All right, so you should press zoom 6. Mine doesn't do zoom 6, so I'm just going to graph it. Zoom in, right? Zoom in to find the fact that you do have these two intersection points, okay? All right, so for your calculator, you press second calc, you will find the intersection points. So second calc, there's number 5 is intersect, and then you find where they cross. So first point there is at 0.1782180.487. I would actually write that down and then store that as a alpha A and then an alpha B for the second intersection point. Or if you want, you can just kind of write it down on your paper and you can use it later, right? Same thing with the second intersection point. You got to do the same process again. So it's going to be second second calc, and then go to 5 intersect. And this one's great because the intersection point is 1, so that's much easier. So the only one you really need to know is the first one, okay? All right, so let's go back to our point here. So point A is 0.1782, I can't read my own writing, 21805, right? And then point B is 1, so that's easy. So the area of R, remember you got to figure out which one's top, which one's bottom. So here you can see R on the top is bounded by G of X, bottom is bounded by F of X. So for part A, my work will be the area, or actually not A, R, because you're looking for the area of R. R is equal to integration from 0 to the point A, top being G of X. So G of X minus F of X dx. Use your calculator, punch the whole thing in, use math 9 and figure this out and get your decimal to be 3 decimal places. So you should get the answer to be 0.06475, which rounds to about 0.065 for 3 decimal places, okay? For S, it's very similar. You're looking for the bound from A to point B. B is 1, so you don't need to write B anymore. But this time F is on top and G is on the bottom, so F of X minus G of X. And again, put in those functions. Don't just put F of X and G of X. So put in F of X as your 1/4 plus sine pi X, and your G of X as 4 to negative X, right? So again, put it in. You should get about 0.41036. This does look a lot bigger, so bigger area. So roughly 0.410 for 3 decimal places. Okay, so now you got to look at this and say, all right, part C says we're gonna generate the solid when S is revolved around the line y equals -1. So this picture is a little too big for me. So if you want to, just kind of really quickly sketch this out. Here's your axes, right? And here's your shape of S right here, kind of looking like this. Y equals -1 is down here. So this is where you're going to revolve it around, right? So that means then you're going to spin this whole thing around. This is a washer method because you have your big radius here. Here's your big radius because it's the farthest away from your axis of revolution. So your big radius is going to be your F of X minus a -1, top minus bottom. So it's really F of X plus 1. Your little radius is this distance right here. So it's going to be your bottom function, g of x minus -1. So g of x plus 1. All right. So then the volume of this, right, this is a dx function because this is perpendicular to our axis revolution. So it's a washer method. So our volume is going to be from a to 1, right? Big radius, f of x plus 1 squared minus g of x plus 1 squared dx, right? And don't forget your pi because pi r squared, right? So again, getting all this out, including multiplying the pi out, your answer should be 4.559. Okay, so again, make sure your mode is correct. You should be on radians, and then your answers will match nicely. Okay, moving on to part two, number 2. This is a beautiful polar equation that we've never seen before, but it's okay. The curve above is drawn in xy planes described by the equation in polar coordinate r equals theta plus sine 2 theta for 0 theta between 0 and pi, where r is measured in meters and theta is measured in radians. The derivative of r with respect to theta is given by dr over d theta equals 1 plus 2 cosine 2 theta. Okay. A says find the area bounded by the curve and the x-axis. So this one's pretty straightforward. This is a polar graph. So 0 to pi goes from 0 to pi, right? So this is the whole area bounded by the curve and the x-axis. Okay, so that means then what you need to do is simply put it into your formula. So for part A, your area is going to be 1/2 r squared, right? So 0 to pi, r squared d theta. So what's your r? R is right here. Put in your r. So 1/2 theta plus sine of 2 theta squared d theta 0 to pi. You don't have to change your calculator to polar form. If you keep it as Cartesian, the only difference is that your variable is now x. So if you put it in as x, that's totally okay because it's all matching. The only thing you don't want to do is put x here and put theta here, right? So as long as your variables all matching, it really doesn't matter what your setting is when you're doing math 9 to figure this out. Okay, so when you put in math 9, you should get this to be approximately 4.382. So actually work these out so that you know you're getting the same answer as me. Don't just assume that what I'm getting is right. And also make sure you can practice the methods on your calculator. Okay. All right. Part B says find the angle theta that corresponds to the point on the curve with the x coordinate being -2. Okay. So x is -2. X is also defined in polar as r cosine theta. So that means r cosine theta equals -2, right? So now I have my function, right? I have my function r. So in my equation, r equals theta plus sine 2 theta. So that means theta plus sine 2 theta, that's my r, times cosine theta equals -2. So again, you can put this into your calculator as a Cartesian equation. So if you put a Cartesian as y equals x plus sine of 2x times sine of, times cosine of x, right? That's y1, and then y2 equals -2. See where they intersect, and you'll get your answer, okay? So you get your answer. If you put it in polar, I don't think it works this way. So I would really keep this as Cartesian. So once you solve, your x is still a theta. So your theta is equal to 2.786. Okay? All right. For theta between pi over 3 and 2 pi over 3, dr d theta is negative. What does this fact say about r? What does this fact say about the curve? All right. So if dr d theta is negative, right, we know that if the derivative is negative, that means the function itself is decreasing. So that means r is decreasing. Okay, so that means in polar, that means your curve is getting closer to the origin. Makes sense. If r is bigger, you're getting farther away from the origin, right? Here's your origin right here. If r is smaller, you're getting closer, coming back. The radius is shorter, right? Because r is radius, it goes out this way. So if r is big, you're going out farther, but r is getting smaller, you're coming back closer to the center, right? Makes sense? All right, and then what does that say about the curve? Oh, the curve will already answer the question. So the curve is getting closer to the origin. Okay. Last one, find the value of theta in the interval between 0 to pi over 2 that corresponds to the point on the curve in the first quadrant with the greatest distance from the origin. Justify your answer. So we want the greatest distance. That means we want to find the maximum, right? So maximum means the derivative somehow. So when you want to find the maximum of something, you could take the first derivative and set it equal to 0. Well, we do have the derivative. We have the derivative right here. So for part D, we take dr d theta, set it equal to 0, right? So in this case, 1 plus 2 cosine 2 theta equals 0. You can do this by hand. Actually, it's a lot easier doing this by hand than to use a calculator. So you get 2 cosine 2 theta equals -1. Cosine 2 theta equals -1/2. So what does that mean? Well, when is cosine -1/2? Well, cosine is -1/2 in quadrants 2 and 3. So -1/2, that makes it pi over 3, and what's the other one? That would be, no, sorry, 2 pi over 3 and 4 pi over 3, right? So you have your 2 theta equals 2 pi over 3. 2 theta equals 4 pi over 3. So then divide by 2, you get theta equals pi over 3, and theta equals 2 pi over 3. Now be careful, look at your interval. Your interval says between 0 and pi over 2. That means one of my answers is moot because that's not in my interval. So the only theta that works is pi over 3. Okay, all right. Next one says, these are very typical. They give you a table of values here, okay? A metal wire of length 8 centimeters is heated at one end. The table above gives selected values of the temperature T of X in degrees Celsius of wire X from the heated end. The function T is decreasing and twice differentiable. They say that because then now we can use any of the rules we have in calculus because all the rules apply when the function is differentiable. Okay, it says estimate T prime of 7. Show the work that leads to your answer, indicate units of measure. So T prime of 7, this is T of X, right? So you want the derivative, it's the change between the 6 and the 8. So T prime of 7 is equal to T of 8 minus T of 6 over 8 minus 6. It's the average change between those two. Typically, we'll find the derivative, but since we don't have the derivative, we only have the table values, we use the slope idea to do this. So we get 55 minus 62 over 2. That gives me -7 over 2. All right, what does this mean? Units of measure, so it's a change. It's a degree change per centimeter, right? So it's going to be, let me write it a little bit bigger here, -3.5 degrees Celsius per centimeter. So that's a change in temperature per centimeter, okay? All right, write an integral expression in terms of T of X for the average temperature of the wire. Estimate the average temperature of the wire using a trapezoidal sum with 4 subintervals indicated by the data in the table. Indicate units of measure. Okay, I'm going to scroll up just a little bit so I can see the problem and have some space. Okay, so part B says write the integral. Well, average value is 1 over b minus a integral a to b f of x dx, right? So in our case, that is going to be 1 over 8 minus 0. So there's too many things a circle here because my whole interval goes from 0, 0, all the way to 8, right? So it's going to be 1 over 8, 0 to 8, T of X dx, like so. Right? So that's the integral version. Now it says use trapezoid, right? So that's an integral expression. So I wrote my integral expression. Now you're going to use a trapezoidal sum to estimate this piece only because you don't have the actual equation to this. You can't do this piece using calculus. So you're going to use trapezoidal sum to do this. Now be careful because if you look up top, these equations are not equal intervals. So you can't use the normal trapezoidal sum. You kind of have to figure out the trapezoid one by one. So that's kind of the fun part. Okay. So the first trapezoid I'm going to deal with is these two. Okay. So it's going to be 1/2, right? Base 1 plus base 2, base 1 plus base 2 times height over 2. So 1/2 is already here. My height is 1 because it's 1 minus 0, right? And then base 1 plus base 2, so 93 plus 100. Okay. And then the next two is these two. All right, so the height is 5 minus 1, so that's 4 over 2. And then base 1 is 70 plus 93. And then the next two, the difference is 6 minus 5 is 1, so that's your height over 2, base 1 plus base 2. And then the last two is going to be 8 minus 6, so it's 2 over 2, 55 plus 62. So that's the correct trapezoidal estimation for this, all right? So plug it all in. Don't forget to make sure at the end, divided by 8, because that's the average value of this. So you should get your average value in the end to be 75.688 degrees Celsius. So that's the average temperature over the whole thing. Okay. Next, find the integral of from 0 to 8 of t prime of x dx indicated units of value, a measure. Explain the meaning of this in terms of temperature of the wire. So, part C, 0 to 8 t prime of x dx. Okay, so while it looks a little intimidating, think about the fact what it means. This is really going to be t of x, because the antiderivative of t prime is t of x. Evaluated 0 to 8, so that's t of 8 minus t of 0. Right? So t of 8 minus t of 0, that means I am looking at the change from the beginning, the difference between the beginning and the end, basically. So t of 8 is 55, t of 0 is 100, right? So you have your 55 minus 100, so negative 45 degrees Celsius. So what is that? That is the total temperature change from the beginning to the end, right? So the total temperature change is that it dropped 45 degrees from one end to the other end of the wire, okay? All right, last part. Are the data in the table consistent with the assertion that t double prime of x is greater than 0 for every x in the interval 0 to 8? Explain your answer. So we're looking at the second derivative, seeing if that if the second derivative is going to be positive the whole time. So I am running out of space. I'm going to use the top here so that I can still keep all my work here. All right, so let's see. The thing about this is that you have to look at it in terms of each of the interval, right? So you have to look at second derivative as the change in the first derivative. You have the original function here, so you have to look at the change in the slope first, and then look at the change in the function by looking at the slope, and then look at the change in the slope to look at the second derivative. Okay, so between 0 and 1, what is happening? So between 0 and 1, the temperature went down 7, right? So in 0 to 1, the change is negative 7. In the next interval between 1 to 5, the temperature went down more. So it went down negative, well, the average, not the whole thing. So it went down negative 17 divided by 4. No, sorry, not 17, negative 23. Sorry about that. Negative 23, it went down negative 23 minus 23 divided by 4. So the change is negative 0.575. Okay. And then next interval between 5 to 6, it went down 8 degrees over 1 second. So between 5 to 6, the change is negative 8. And then the last interval between 6 to 8, that's 2 centimeter difference, and the change was negative 7. So negative 7 divided by 2 is negative 3.5. Okay, now look at the change. From negative 7 to negative 5, what happened? It actually went less, right? So the change is positive. And then from negative 5 to negative 8, it went down more, so the change is negative. Then from negative 8 back to negative 3.5, the change is positive. So is my second derivative always positive? No, because my second derivative is positive, but it's negative and then it's positive. So you can say for a fact that the second derivative is not greater than 0 in the entire interval of 0 to 8. And you can kind of talk about this a little bit more. Simply a table like this is not really enough, but this will help you with your wording on how to explain why this happens. Okay? All right. Last problem for today, it is the differential equation of 2x minus y. Oh, these are fun. So it says on the axes provided, sketch a slope field for the given differential equation at the 12 points indicated, right? And then sketch a solution curve that passes through the point 0, 1. Okay, so the beauty of this is that since there's only a few points here, you can actually do these fairly quickly. But let's do the quick ones first. For example, I look at the one on the x-axis. On the x-axis, your y value is 0. So that means you're only looking at the x. So that makes it a lot easier. So you're looking at 2x here. So I can just look at these numbers and go, okay, well, 2 times 1 is going to be a positive 2. So it's going to be a little slanted. 2 times 2 is going to be a positive, sorry, not that way. One more time. 2 times 1 is 2. So my 1 is going to be 45 degrees. My 2 is going to be a little slanted, right? And then 4 is going to be even slanter, so steeper. All right. Next part, on the other side, I have negative 1 times 2. So it's going to be negative 1 times 2 is going to be slanted on the other side. Oh, I forgot 0. 2 times 0 is 0. So that's still horizontal. Yes, you need to show this one, right? The only time you don't show is 0 over 0. Okay, what about the y-axis? So on the y-axis, I know that your x is 0, so it's just looking at the negative y. Okay, that makes it easier. So at 1, it's going to be a negative 1, so there you go, perfect. And then at 2, it's going to be a negative 2, so steeper here. Okay, all right, so now the only ones I have to work out are, let's see, 2, 4, 6, 6 points. That's not so bad. Okay, so at let me see if I can get this a little bit better. So I got negative 1, 1, negative 1, 2. I like to line it up so I can see the points pretty nicely. 1, 1, 1, 2, and then 2, 1, 2, 2. Okay, and then I do the math. So this one says negative 2 minus 2, so that's negative 4. Negative 2 minus 1, negative 3. Okay, so it's going to be negative 3, negative 4. So steeper and steeper. Okay. All right, and then next one I get 2 minus 1, so that's 1. So that's a perfect 1. And then this is 2 minus 2, so that's 0. Okay, 0 here. And then next one I get 2 times 2 is 4. 4 minus 2 is 2, so steep. Okay, and then I have 2 times 2 is 4. 4 minus 1 is 3. So, okay, so that means, if I remember correctly, this one was a 4. And then so this one is a 3. This one is a 2. Okay. Yeah, it's a little harder to see what it really is, but it's okay. All right. Next, it says to go through the point 1, 0, 1. So 0, 1 is here. So if I follow this, it looks like it's going to slant here. And then it's going to go here. So there's a 0 in there somewhere. 0 is probably no, sorry. 0 is probably in here somewhere, but it's not on an exact integer point. So that's why we can't really see it. But we know there's a 0 because seeing the other ones, there's a 0 there somewhere. So we know it's going to be kind of like a parabola-ish curve. Okay. All right. Next, the solution curve that passes through the point 0, 1 has a local minimum at x equals natural log of 3 over 2. What is the y-coordinate of this local minimum? Okay, so local minimum, I'll work it out here. The local minimum means that your dy over dx is equal to 0, right? So that means my 2x minus y is going to be 0. If you solve for this, you get y equals 2x, right? So what is the y-coordinate? Well, the y-coordinate is going to be 2 of this x value. So y is going to be 2 times natural log of 3 over 2. That's a number. So not very pretty, but that is the answer. Okay. All right. Part C says that y equals f of x is a particular solution of the given differential equation with the initial condition f of 0 equals 1. Use Euler's method. Oh, I need more space, so I'm going to clean this up. Use Euler's method starting at 0 with 2 steps of equal size to approximate f of negative 0.4. Show the work that leads to your answer. Okay, so remember this Euler, I usually make a t-table so I know where I'm going. All right, so x, y. Euler starts at 0, 1. It says 2 steps, so it's going to negative 0.4, so it means negative 0.2 to get there, right? Okay, so Euler says that we have our y value, y2. The second y value is going to be the first y value plus my step. My step is negative 0.2 times my derivative of the previous point. So 2x minus y. So 2x is 0, minus y is negative 1. So it's going to be 1 plus 0.2. So 1.2 is my second point. All right. All right. Y3 is going to be the previous y, so 1.2, plus my step, negative 0.2. Remember, it's a negative step because it's going down negative, right? Times, okay, 2 times x. So that's negative 0.4 minus 1.2. So minus 1.6. Okay. All right. So then that gives me 1.2 plus that 1.5, sorry, 1.2 plus 0.2 times that. So that's going to give me 0. What? 0.2 times 1.6. That is going to be 32. So 0.32. So that gives me 1.52. Okay, 1.52. So then that's it. So that is my answer. My y value is 1.52 at the point of negative 0.4. Okay. All right, last part. Find the second derivative in terms of x and y. Determine whether the approximation found in part C is less than or greater than f of the actual value of negative 0.4. Explain your reasoning. So let's find the second derivative. So since y prime equals this, so dy d squared y over dx squared equals 2 minus y prime. That's 2 minus, remember we can't keep it as y prime, so we got to plug in the y prime back in. 2 minus 2x minus y. All right, so that gives me 2 minus 2x plus y. All right, so now we're going to see. This is in f of negative, sorry, my point that I'm looking at is negative 0.4 comma 1.52. That's your point, right? That point is in quadrant 2 on a Cartesian plane. It's right here, quadrant 2. In this quadrant, your x is negative, your y is positive. So if x is negative, this is going to make it 2 plus a positive number plus a positive number. That makes my second derivative, y double prime, greater than 0. So it's going to concave up. For concave up, your tangent, because it's a derivative, your tangent is always going to be underneath it, right? So concavity, your tangent is going to be underneath it. Therefore, your tangent, because it's under, it's going to be an underestimate. So again, concavity tells me that if it's concaving down, my tangent is going to be above, so it's going to be an overestimate. All right, so then we say that your support for this is that since y double prime is positive, this is concave up. Therefore, your dy dx approximation is underestimate. Okay, all right, that's it for this part today. All right.